I happened to look in some old rags for last year, and I realized it's exactly a year since Andy last presented to us. Last December, he gave us a great presentation. And one of the things I always like about amateur radio is it doesn't matter how long you've been a ham and how many things you've done, you find stuff that you know nothing about. And for me, tonight is one of those. I've never heard of Pluto. My daughter tells me it's a planet, and I tell her it's not a planet. But apart from that, I know nothing about this. So I'm looking forward to learning something about it. Hopefully, the technical problems will be with us over in a moment.
That's fine. That made it easier for me. All right, I think everybody can
Thank you,
see
Andy, and thanks for everybody's patience.
Yeah, things happened, so there was a backup. All right, I'm curious, just how many people here, I guess including online, do we need to share? Yeah, I don't think I'm curious, how many people here and online have a Pluto SDR of some form? Is anybody here in the room? All right. How about online? I'm curious if anybody has played with one of these. Show of hands. What do we got? Crickets. Okay, this may be new for. How many people have heard of this thing? All right. Okay. So we got all right. Some familiarity. Now, I have a feeling that at this point, I asked this question 10 years ago, but how many people own an SDR of some sort? Yeah, okay. So like over half the room here, and I'm going to guess that's representative of online. So they're going to be, when I used to talk about SDRs, I had to like go through this whole thing, like, what is this thing? Like they're kind of like these black magic boxes. Now they're black magic boxes that everybody has. So we got that going for us. All right, so a Pluto SDR, there's gonna be things that are familiar to you. If you, how many people have one of those little SDR dongles, like RTL SDR, played around with that? Yeah, okay. There's gonna be some cool stuff in here that actually applies to that as well. So if you've played with one of those, some of this is actually gonna be familiar. All right, anyway, this is what a Pluto SDR looks like. I stole this from the Analog Devices marketing slides. According to Analog Devices, this is kind of how they advertise the thing. It's a portable, self-contained learning module. Right? ADALM is Analog Devices Active Learning Module. Like Apple computers, they want to get these things out into the education, out into largely universities, colleges, things like that. It's a place to learn about SDRs. They go through here and say RF coverage from 325 megahertz to 3.8 gigahertz, which is a lot of band. I mean, that's really broadband by anybody's measure. When we think about the radios that we use, they tell you, yeah, you can look at 20 megahertz of bandwidth. They go into ADC depths and all this kind of stuff. And then they really, you can tell they're going to education market here. MATLAB, Simulink support, GNU radio, a bunch of languages, drivers, all that good stuff. If you are in the EE program or software engineering, this is for you. Here's how I think of it. I think of it as a transverter on a chip. All right, we're going to see what that really means. Basically, when you break this thing down, it's got tunable local oscillators and some mixers on there. It just does frequency conversion, right? That's familiar to all of us, right? You know what a superhet radio is. You got a mixer. You take high frequency, move it down to low frequency. At some point, you've moved it low enough that you can hear it in your headphones, right? This thing goes both ways, like your transmitter and receiver transceiver does. You can mix up or mix down. The big difference here is that the intermediate frequency is a stream of digital samples. So instead of taking 144 megahertz and converting it down to like, baseband or something like that, really what you're doing is you're converting it down to baseband, but instead of getting out as audio or as RF in this case, we're just going to send it to your computer. And the last leg is going to be some sort of software processing that's going to turn it into something that you can see or hear or whatever it is you're trying to do with your radio. But in the end, it's basically a direct conversion receiver. All right, so all we're doing is mixing down to a low frequencies, turning it into bits and sending it over USB. All right, here's the block diagram. If you look at the top there, that's the RF side. The bottom side is all the exciting digital stuff. So what you've got there is there's a transmit side on the left and a receive side on the right. So it goes out on the left, comes in on the right there. Pretty symmetrical, right? You got amplifiers either make your signal louder or to make what you're trying to listen to louder. That's your low noise amplifier on the receive side. You can see the mixers. There are filters. You notice there's the DAC, digital to analog conversion, or analog to digital conversion. All right, you can see that's where we've gone from RF into digital land. So your mixer is going to down convert it, and the filters you see below that, the filter and the finite impulse response, the FIR filter that's there, that's done in the digital domain. So you've got filtering happening on the top in RF, and you've got filtering happening on the bottom in software. The bottom block that you see there is all the exciting software-y things like drivers, what the interfaces are, how you actually talk to this thing from a computer. So if you are, interested in the software side of things, talking to this stuff, that's where you're looking. We're going to have another slide on that in a second. Don't worry, I don't expect you to remember all of this stuff. I just want you to see that analog on the top, digital on the bottom, actually pretty simple. Yeah. You want to blow up that RS section because we're all hams. We like RF-y things. You'll notice that there's a whole bunch of inputs over there. There's an RX1, RX2. There's actually 2 receivers on here, 2 transmitters. A bunch of amplifiers. There's your mixer. They got a common local oscillator here. Cool thing here is you can do this at the same time. You got one transmit chain, one receive chain. Yeah, thank you. Here, I can point. Look at that. All right, so you can run them. You've got your receive here, your transmit here. You can run these 2 independently, and you can run full duplex if that's something you want to do. You want to make a low-power radar in your basement. This is the way to do it. Fun stuff. Use your imagination, right? Which is kind of what they want you to do in the lab, right? This is why they want to sell it. This is student projects, exciting things like this. All right, like we do with most expensive toys, we take the cover off and look inside. Got another slide here. So let's zoom in on the exciting part here. So here are the parts that matter. The 809363, that's the top block that you saw there. That is the RF to digital conversions all happening in there. It has a Zinc processor that's basically a small FPGA and a couple of CPUs that are in there, so you can run software on this. It's got some memory, it's got some flash because it's running a small Linux kernel inside of here. So it's got a little computer, it needs all the parts that a regular computer would have. That's the main hardware. Now, let's see. You'll notice here that these are the 2 SMA connectors. This is your transmit port and your receive port. You'll notice there's actually 2 more here that aren't hooked up. If you remember that block diagram, there's another transmitter and receiver that's available. Analog Devices was very nice. They decided that you get more than they actually advertised. You'll see why in a second here. They spec this thing, like I said, to 325 megahertz to 3.8 gigahertz. In reality, this is probably a bin to 809361, which has a much wider bandwidth. So if you've looked at any of these things, you know that you can hack them and open up the frequency range. Doesn't make it an 809361. Doesn't mean it'll meet spec for that, but it'll generate RF and you can hear there. And I mentioned that's the FPGA. It's a Zinc 7000 series and a couple of small ARM processors in there. All right, runs Linux. It's got a U-boot bootloader. If you're familiar with those things and like to play with them, they're there. It's open source. Have fun. Here's our front end. Like I said, more than advertised. They were even really nice. Not only did they bring out these extra transmit and receive ports, but they actually glued down the balun that goes with them. So they didn't have to do that. A lot of dev kits you get, the pins are exposed. It's up to you. No, they actually put parts down to make it usable. If you notice at the bottom here, there's a clock input. So you can actually supply a high stability reference oscillator for this if you want to run this at high frequency for microwave narrowband work that, I don't know, hams might be interested like me. So you can bring out those extra connectors if you want. That's a state. You can get pigtails for that. You've probably seen these UFL connectors on like routers and things if you've ever been inside there. Pretty standard. Puts out something on the order of a milliwatt. A little more where it's spec to be, where it's actually spec'd, and less when you take it out of its spec range. But on the order of about a milliwatt is what you can get out in terms of transmit power. On the receive side, the noise figures here are actually pretty decent. A lot of people say, whoa, 10 dB noise figure, that sounds kind of lossy. Well, it turns out if you get to 5 or 10 gigahertz, you're already looking at a mixer that's probably got 8 dB of loss in it already. So we deal with this with low noise amplifiers. So it's really not anything that would be a significant performance impact. And they've got some other specs there. You might want to keep strong signals out of it. It's not super good from an IP3 perspective, but that's what filters are for. We're going to talk about them in a little bit. All right, for you software guys out here, this is how you talk to the thing. Basically, they have the drivers running in Linux here. You can write software that actually, runs on it, that all by itself is standalone. What most people do is they use this USB cable, and it plugs into the Pluto, and you run all your processing software on a separate PC. All right, and that's what that dotted line here. That network link, it actually just shows up as an Ethernet interface when you plug in the USB cable. So it's all actually TCP/IP for the communication. And if you use any of the other software, like SDR Angel or anything that can talk to this, it's just using IP-based stuff. All right, as I mentioned, hacking this thing, they actually encourage you to do this on the Analog Devices website. So go and hack. An example, all right, let's make it an 809361. So what we do is we just tell U-Boot, hey, you're an 809361. Open up those registers for me, because we know it's the same die, Analog Devices. And you can tell it to turn on the second receiver, second transmitter. You can tell it to you make it an 809361, it'll run from 70 megahertz to 6 gigahertz. So that's where you can actually use this thing. Reboot it, and from then on, it'll play from about 70 gigahertz to 70 megahertz to 6 gigahertz. I'll just mention there's another version of this out there. Supposedly a slightly improved. You can get this off of Alibaba and eBay. I don't know a whole lot about it. You get a metal case, which is nice, and it's got a better TCXO inside, so the frequency is much more stable. These things are, if you want to use them up in the microwave range, you need something that is stable. I can bring up, when we're done here, I have a system that I use an external GPS clock for it. This one's probably good enough, at least at 5 gigahertz, that you could use it for something like CW and single sideband at 5 gigahertz, at least beyond frequency. It might drift a little bit, but not significantly. All right. So what can you do with it? All right. Well, first of all, it's got a microwave receiver in it, so presumably we can at least make a narrowband spectrum analyzer out of the thing, right? We can look at 4 gigahertz at a time. 4 megahertz at a time, maybe a little more than that with a good link, but that's kind of what you're looking at. It's good for looking at signals, right? Going the other way, obviously, it's a nice lab signal generator. It's fairly easy just to generate something from 70 megahertz to 6 gigahertz. That's really quite useful. I used it to bring up a 24 gigahertz transverter. I needed to inject some weird, 2200 megahertz signal at an IF and measure something. Well, this thing does it. That's kind of nice to do that. You have both a transmitter and receiver that work together, so you can have a network analyzer if you want. Maybe going a little further off field is you can actually turn this thing into a portable antenna range. If you like to measure antennas, particularly at UHF and up, this is a good way to do it. And we actually did this at the Rochester VHF group August meeting. I got some pictures from that. And what it will probably do is I have a demo. We can do that in the room when I'm done here. So you can actually see how that works. I got a signal source set up. Now, of course, what you're all thinking is, well, I've got all this frequency coverage. There's like 8 amateur bands that fit easily within there. Why don't I just make a transceiver out of it? So we're going to do that. First, I'm going to mention some of the more, I consider this stuff mundane now. I mean, how many people have a network analyzer somewhere, right? A tiny, one of the tiny nano VNAs, right? Right. I mean, they're pretty ubiquitous now. Like what, $50 you can get this sort of thing. Yeah, and it works. It's good for looking at things. You know, I don't think this is going to be any kind of precision instrument, but there's some pretty neat software out here. This guy, IU2KVL, put together some software that will actually stitch together over a wider bandwidth. You can only get 4 megahertz at a time, but there's no reason you can't just sweep really quickly at 4 megahertz chunks and then, you know, look at, I don't know, 100 megahertz, right? So he's got software that does that. If you want to get yourself a directional coupler, you can have a VNA out of it, so you can get the phase information as well. So that's pretty cool. He also does some things with harmonic sampling if you want to look higher in frequency. All right, let's talk about an antenna range. And this is my idea of an antenna range here. Has anybody here been to you know, like a VHF conference or something where somebody's actually taken antennas out in the parking lot or out in the field and actually measured gain? All right. Okay. So we're going to go through some basics on how this works. If you look at this top diagram here, there's a transmitter over here on the left and a receiver over on the right. Basically, what you're going to do is you're going to transmit a signal, receive it with a known antenna of known gain. This is harder than it sounds, but some sort of reference, right, that you're going to compare everything to. All right, and the trick is you want to get everything out in dB. So the way this has been done, probably for, I don't know, 70 years, is your signal source, you just start with some sort of RF oscillator, and you chop it up at usually 1,000 hertz. Okay, so this is what a pin modulator does. It's basically AM modulating to make 1,000 hertz pulses. All right, so if you return an AM radio there, you'd hear a tone at 1,000 hertz. That's what it does. On the other side, on the receive side, what you do is you basically have a glorified crystal radio. All it does is rectify that signal and turn it into DC. I've blown this little diode section up here, down here. You'll notice that, diodes are not 50 ohm devices, all right? But we typically work with 50 ohm systems. So these little detector diodes usually have a 50 ohm load in front of it. So your antenna looks like it's, you know, thinks it's looking into 50 ohms. So you get a nice, you know, you get a voltage in reference to that, and that's what you end up rectifying. So that's really what's going on down there. This works from DC. I've seen this actually used at 122 gigahertz on an antenna range. Now it's a diode sitting in a piece of waveguide, but that's exactly what you're doing. You're just rectifying a signal. All right. The trick is a square law detector, right? You got to run the diode in a square law region, and so if my signal goes up, by the time I've AM modulated, I can read out in dB on a selective level voltmeter. So it's really simple technology. All right. It does have some problems. Detection's really broadband, right? There's no filter on this thing, as you guys noticed. So if you have interference from other RF sources, a big one used to be the video sync. If you had a nearby television transmitter where you were trying to do this, it would get into that diode and you see your meter go up, but you weren't looking at the signal that you were generating, you were looking at the TV station. Which would mess up all the measurements. Another thing is there's only a certain region where these diodes are in that nice square law region. If the signal gets too loud, it starts to roll off. And if it gets too little, you don't have enough to detect, and you have signal plus noise to noise problems. Okay, so you kind of have to be in this like 30 dB happy range. This is a problem sometimes because you might have a reference antenna, you know, let's see, like this one here. And this is about 6 dBi, all right? If this is the only reference antenna I have, I take out my 2-foot dish, which has about 30 dBi a gain, you're going to have trouble keeping both of those antennas in that linear region. So that's a problem we run into. If you do this with surplus equipment, because that's all I can afford, this ends up being kind of clunky. These things have weird voltages sometimes. You get a surplus oscillator that wants negative 24 volts and fun things like that. So it can get a little bit clunky. All right, there's a few parts you gotta put together to make this happen. All right, so that's the old way. So I'm going to do this with an SDR. Let's just do this in software. The idea, kind of the goal here is to use processing gain to make a power detector that just beat the pants off a diode. All right, it can listen to a weaker signal. I don't need a calibrated RF source to do this. I just need a signal source. I don't even need any modulation. I just need a carrier. Turns out it'd be really nice if it doesn't even have to be that stable. If you've ever, done anything at microwave frequencies, stability can be a problem. I mean, you can't just multiply a crystal sitting in air, 100 times and expect it to stay on frequency at 10 gigahertz. It doesn't work that way. So if you don't have an ovenized source or something like that, that's expense. There's more clunky things, power supplies you got to bring in to run all that. So simple is good. And we want something that's got a lot more dynamic range and to be more linear than a diode detector. All right, lightweight, everything runs on batteries. So this is what we do. I just use a standard signal source out here, the DigiLO. Actually, I have it over here for you guys in the room. This right here is a signal source. That's a DigiLO. All right. What it does is it provides a signal on every amateur band from 10 meters to 5 gigahertz, and then of course you can use harmonics beyond that. So you want to use a harmonic of 3 gigahertz at 10 gigahertz. You can do that. And I kind of give you some ideas of the signal strengths that come out of this thing. So you get about on the order of a milliwatt, and then it rolls up by 5 gigahertz. It's like minus 8, minus 10 dBm. So you're down at 100 microwatts. And then obviously harmonics are going to be less than that. All we're going to do is detect that over with a Pluto SDR. This pad in here is the same reason you have that 50 ohm load on the detector diode. Turns out the inputs to these SDRs aren't really 50 ohms. If you look at them with a network analyzer, you're going to even in band where it's spec'd, you're probably going to see an SWR about 2 to 1. If you want to take it up to 5 gigahertz, I can guarantee you this thing isn't anywhere close to 50 ohms. And we're even going to go a little bit beyond that. But the whole point is I want my antenna seeing 50 ohms so that I don't have reflections and things like that messing up my measurements. Right? And then we're going to write a little bit of software and just read directly off in dB. All right? And there's a little complexity in the software, but it's really it's a spectrum analyzer that does a good job of measuring the signal level. All right, here's some things I learned from doing this. First of all, it's good to know your FFT window functions. If you don't know what that is, that's fine. Basically, it turns out when you want to measure a signal using an FFT, you have to worry about what happens when the signal gets in between FFT bins. If you ever watched a drifting signal on your pan adapter, and it kind of does this, like a really strong signal as the signal drifts. You guys know what I'm talking about? Maybe you've never seen this. You get spectral leakage, right? The algorithm, will say there's energy that's getting spread across all kinds of different bins. Well, when that happens, energy that should be in one place is measured as being spread out. So the peak of your FFT goes up and down as the signal drifts, which is not good when you're trying to measure to the dB or a fraction of a dB. If you use a good flat top window function, can take care of that problem. Right? And this is what, if you have a spectrum analyzer, a good desktop spectrum analyzer will use a window function like this, and it'll tell you your signal is this strong, 6 milliwatts or whatever it is right there on the screen. That's what it does. It's using a window function to kind of integrate that energy. So we got to do the same thing in software. I mentioned the attenuator. The other fun thing is these are plastic cases. So when you get up into the microwave region, it turns out the PC board actually can make a pretty good antenna. So there are limits to kind of the dynamic range with the antenna. Like if you're trying to measure front to back ratio, where you want to find how deep is the null in my antenna, well, at some point you're probably going to have a better antenna inside this than you are on the antenna. There are solutions for this. Put it in a box, for example, or maybe get the one that comes in a box, the Chinese one, the Pluto Plus. I imagine that'll make things much better. Here's the software magic. I've got this on my other computer. What I'll do at the end of the presentation is I'll bring this up, and we're going to measure an antenna. And I brought this in because I want you guys to know that at microwaves, you can get away with murder. All right. So this is a transition I made out of a soda can. Right. Waveguide to coax transition. It's ugly, but it actually does work pretty decent. Certainly good enough to do a demonstration here. I couldn't find my WR229 transition, so that's what it is. But we'll compare that to my PC antenna here in a little bit. All right. Here's a picture from the August tune-up clinic. And if you look carefully at this picture, I think I'm proving to somebody that you can take an end connector and jam it into a BNC. Yeah, I'm really getting into it there. This is on Jared KF2MR's 5 gigahertz dish. We're measuring the gains. The way this gets set up, we wouldn't do it like we do it in here. This would be a terrible place to actually set up an antenna range. What you want is a nice open field with no reflections and things like that. We actually put because ideally I'd have a nice tall tower and just be looking off into free space. The next best thing is to get that antenna right down at the ground and basically have your reflection point right at the antenna. So that's what we do from a practical perspective. And it was a really nice day, and it wasn't wet out there. It was wonderful. We did 900 megahertz to 10 gigahertz. You notice I did, yes, that's not a typo. I did use the Pluto at 10 gigahertz. We'll talk about that. We found a lot of dBs. All right. Adjusting a dish antenna is kind of like magic. You just have to get the focus in the right place, and it's never where you actually measured it to be. There are a host of reasons for this. The best thing you can do is get a signal source out there and tweak it. Tweak time is the best thing you have. And what was great is I could let people just sit there with the laptop and adjust and watch the screen, peeking up the antenna. So that was kind of cool to see people actually using it that way. I could kind of be hands off. We found there were some really good dishes in the area. So if you want to learn how to build a microwave station, Rochester is the place to be. Okay, but 10 gigahertz. Yes, the nosebleed section of amateur radio. All right, the Pluto doesn't go to 10 gigahertz. All right, it's spec to 3.8 gigahertz. We can tell it to go to 6, but how in the world do we get to 10 gigahertz? In fact, my signal source doesn't actually go to 10 gigahertz either. All right, so we do a signal processing trick. All right, first on our signal source side, we use the third harmonic of the signal source. I tune it to 3456, which used to be part of the amateur band at 9 centimeters, and we just multiply that up by 3. So I can use the harmonic directly. If I need a little more signal, what I'll do is I'll just get myself, a little surplus amplifier and just drive the snot out of it. Get a square wave, get all those harmonics out there. Stuff you're not supposed to do with your own radio, but for approved lab use, yeah, we want harmonics. So we can do that. And then what I do is I put the SDR receiving on the 5th subharmonic. All right. Why would I do that? All right. So here's what's going on. If I'm the receiver and I'm receiving down here at like 2.2 gigahertz, that's 1/5 of 10 gigahertz, I'm actually using an alias. When I sample this signal, I am going to get an alias up at a much higher frequency that's going to look like it's at a lower frequency. All right. Most of your SDRs try to prevent this from happening because this will cause a whole lot of interference. Generally, you don't want to have that. But remember, this is basically a dev kit. There is no filter on the front of this. So it's going to alias if you don't put a front end filter. We're going to use that to our advantage here. All right. So what I can do is use the 5th harmonic, the 5th harmonic of the LO to listen at 10 gigahertz. Well, my signal source is at 3 gigahertz on the 3rd harmonic. And they're not going to crash into each other if I do that. Because that won't go into the math of why that is, but it turns out I'm listening on the other sideband on the 3rd harmonic, so it won't actually interfere with me when I'm receiving. So there's an awful lot of loss in the system when you do this, but the good news is that gain is really cheap. All right, I can just make the signal source a little louder if that's what I need. All right, so I don't actually mind the fact that I've got 3 feet of flexible coax going to my receive antenna that I'm trying to measure. As long as that I measure everything with the same amount of loss, I'm just comparing dBs to dBs, right? I can compare it to a reference antenna. Right. I could probably demonstrate that in here too. Yeah, I don't have the. We'll do the demo later. Let's see. Yeah, okay. We'll get the toys out in a second. All right, how about making a real radio? This was the best picture of a real radio I could find, by the way. I almost thought it was homebrew, and then I looked closer. So the Pluto SDR is a really great exciter. I mean, frankly, it's hard to blow stuff up at 1 milliwatt. All right. You might say, why would I want something that's got 1 milliwatt? Well, the reality is you're going to end up amplifying whatever it is. You're going to end up mixing whatever it is. Those parts tend to be low power. It's really nice to be able to make mistakes because the part is probably going to survive. So I like it for that. What's really cool about this is the transmitter and receiver can go anywhere, and they're completely independent. So, you know, I can receive at one frequency and transmit at another. Why would I want to do that? I don't know. That's kind of how you do satellites, right? I mean, maybe we can, you know, maybe a mixing scheme I can come up with surplus parts. If you want to experiment, there's all kinds of great stuff there. As we mentioned earlier, it covers 8 bands. In fact, it's just like my HF transceiver, except for microwaves. And the whole point is there's a lot of surplus parts out of here. So if you like to build stuff, this is a great place to start. You get a signal and you get a receiver and you can start working with filters. There's a lot of stuff you can build on your own, especially if you're mechanically inclined. There's a lot of stuff you can do. The problem I've always had is that SDR software is not exactly user-friendly. It never felt like a radio. When I'm using SDR software, they're all centered around receiving, a nice big pan adapter display. But if I actually want to sit down and talk to people with it, with maybe a tuning knob or something, I find that really hard to do. And there's not a lot of software out there that has transmit support. All right, so that's where this thing comes in. This is the Langstone software. It was the brainchild of G4EML, and it is what I consider an actual usable radio transceiver interface. I'll fire one up here in a second. CW, SSB, FM. Yeah, I don't think he put AM in it, but he could have. I don't know. I don't like AM, at least not in the microwaves. It's not very useful. 75 meters, it's fine. Fully configurable TX-RX offsets, multiplication. It's got a little band decoder on it, so when you change bands, you can switch to a different set of filters, which you're going to need with a radio like this. If you like working with Arduinos and things like that, this is great because you can take those signals and do all kinds of wonderful things. It's not an IC705 killer, but it's fun to play with. In the end, it's probably marginally cheaper too. It's all GNU radio under the hood. If you've ever played it, has anybody here played with GNU radio? Oh my goodness, we have some. All right, so it's GNU radio under the hood. So this is what it looks like if you put it in a nice case. I can't do anything that beautiful, but I thought it was a nice picture. It's got a Raspberry Pi running behind it, and it uses a touch screen. This just uses a standard Raspberry Pi touch screen that you can get anywhere. Actually, right now it uses mouse buttons for scroll and for frequency control. I actually have an actual mouse connected to this one, but you can actually take the mouse guts out and put it on nice little buttons like this guy here. You can have some fun with that. You'll need a compatible USB sound device for your headphones and microphone. You supply the filters and the switching. So there is some DIY here. It's open source. It's still experimental. I just upgraded to the latest version here. I've noticed some stability issues, but all in all, it's been pretty good. Best of all, if you do this, you're gonna learn a lot, and that's kind of why I got into it. I mentioned that the TCXO that comes in the analog devices one isn't very good. There's that port in there. You'll need to drill a hole. This is a picture of what I did. Just bring an SMA connector out to the end, and you can inject you know, a VHF clock source in there. And it doesn't even have to be anything standard. If you have something off the shelf, you got an OCXO for 57 megahertz, that'll work fine for this. I use a Leo Bodner mini GPS. I love those things. It's one of the best things I have in the RF lab. All right. So last January, this is really for the, no, I did this for not this last September, but September VHF a year ago. I said, you know what? I'm going to go get on all 10 bands, one way or another. So what I did is I just used this little PCB Yagi here for 900 through 3400. All right. This picture shows the big 5 gigahertz dish. You know, this is a surplus, you know, backhaul dish for 5 gig that somebody dropped, so it's almost parabolic. What I did, so I made an actual, I made this a real station for 5760. So I went ahead and put an LNA on the receive path, and I put a 4-watt amp in the transmit path. So this thing's a real radio at 5760. On the other bands, I can work the guys in Rochester if I go down to the road where I don't have trees in the way. And I did actually work with a little 1-watt PA in this antenna here. I did work a couple Canadians on 900 megahertz. So you can actually make contacts with this stuff. Just the bare Pluto by itself, I worked 37 kilometers on 5760 with probably something on the order of 100 microwatts out, and that PCB Yagi antenna. So there are people to work here in Rochester in the contests if you want to do that. Oh, this was fun. So for the switching of all of this stuff, when I switched bands, you know, I had to put relays and stuff in there and all that stuff. And I forgot a back EMF diode. I will tell you, I will never do that again. The back EMF on this thing, it would cause the Raspberry Pi to reset. So, you know, you'd get this little spike of, I mean, who knows, I don't know, 20, 30 volts coming back. Right? There's a big voltage spike on just a little tiny signal relay. And it would cause the Pluto to reset about every 5th time I came out of transmit. So that was a little aggravating. So PSA, don't forget the back EMF diodes. All right, TX performance, I think I mentioned some of this already. There it is, N2WK, I worked at 50 kilometers, which is that little antenna on 5760. And I said minus 4 dBm, I've since measured it, it's probably a little less than that. dBm, by the way, I don't know, maybe that's not familiar to everybody. It means dB relative to 1 milliwatt. Use it all over, you know, RF industry stuff. So 0 dBm is 1 milliwatt. So 4 decibels below 1 milliwatt. You can do the math. A little bit of power. I should mention the TX does not filter the odd harmonics. They're actually not harmonics. These are the aliases on the transmit side, but they look like harmonics if you look at a wide enough bandwidth. So you really do need a filter on this thing, especially if you're going to try to use this at VHF or UHF. You get up into the microwaves, it tends to be less of an issue because if you've got any stage in the middle, you've got waveguide that's going to filter it out. You've got probably a PA that's not going to pass 3 times the frequency you're giving it, but just something to be aware of. That's why I've never really used this thing below 900. Anyway, all right. How about the RX performance? As I said, the noise figure is good enough to make lots of QSOs just with this thing that you get off of DigiKey or whatever it is, wherever you pick it up. You know, it's not a lot of power as people run power on these bands, but there's a lot of people to work in the area if you get on for a contest. I found mine to be really deaf on 5760, so I put a 25 dB gain stage and with a 1 dB noise figure in front of it. That took care of it. So basically, you want low noise front end with a lot of gain, you know, and that's what everybody does at the microwaves. By the way, there's some LNA in front of it just to overcome whatever losses are inside the box. Images can be an issue. So you know, if you're there's a lot of services in the microwave range. You got all kinds of LTE, cell service, backhaul stuff. It's probably good to have a filter if you want to hear really well, especially if you're going to take this thing out in a rover or something like that. You never know. Typically, you end up on a hill somewhere, and what else do they put on hills? You know, towers with commercial services on them. Again, putting it in a box will help. Waveguide is an excellent high-pass filter, and you can use pipe caps too. I didn't bring one in, but it's just another way, making basically a cavity that passes only a narrow band of frequencies. Let's see. Let's move on here. All right, so here's my 5760 DX. I live down near Livonia, and this is I worked VA3TO. He was actually using a 1-foot panel antenna for 5 gigahertz. You know, like you'd have for Wi-Fi, and I think 200 milliwatts. And we were able to easily work each other on CW. And I think that's pretty much an any day, every day, with this kind of power and these kinds of antennas. He was just using a regular Down East microwave. He was using a Down East microwave transverter. We're not hooked up to the internet here, are we? Oh, I can actually play this? You guys in here? I don't know if you guys will hear it here. Probably not. Okay. Try it. Oh. Try it. I gotta take that off. I'm always excited to see what would happen. All right. I'll do that after. How about that? Yeah. We can do that one after. Or I can give it to you on your phone. We'll just move on. All right. Okay. I love this picture. So you can also use this thing as an IF radio, right? So if you are into microwaves and you have a transverter, you can use it like a 2-meter IF. All those problems with, transmit harmonics and stuff go away. You usually got a filter on the front end, going into your mixer and stuff. But I did this for the 10 gigahertz contest back in September, I believe is when I put this one on. Basically, I just drove it, with its 1 milliwatt out or whatever, drove the transverter. The transverter puts out 2 watts or something like that. I had to reduce that greatly to drive a traveling wave tube amplifier to 20 watts. This was what I ended up with. This thing is the epitome of poor engineering. I literally wrote the sequencer to basically switch the amp and the preamp, because you got to be careful. You don't want to get the goes outa into the goes into on these systems. So you got to make sure everything gets switched at the right time. And 20 watts is a lot of power to go to the wrong place, especially at this frequency. So I basically tore into the switch of an old rack mount TWT here. This actually came from an AWA auction. I got it working. And so I skywired this whole thing together with with the lights on Friday night before the contest. I mean, I don't know if you can see this here, but I mean, there's an Arduino screwed down to a piece of wood here and a relay board, and little little push pins going between them. It's awful. It gave me a band scope though. That was kind of cool. I could, you could actually move the dish around. You can actually find people at 10 gigahertz, like search and pounce. It's pretty neat. And Alana over here worked W8BYA on this system at 660 kilometers. Sideband, loud Saturday night. That was cool. That was very cool. Everybody was very excited about that. All right, let's just keep going up, huh? All right, 47 and 78 gigahertz. So here I have to use a mixer, right? What's cool about the Pluto is that I can kind of use whatever frequencies are convenient for me, whatever oscillators I have and mixing scheme I can come up with. So surplus oscillators on weird frequencies that nobody wants for dirt cheap on eBay work great for this. So I was able to get this thing working with a 288 megahertz IF for 47 gigahertz, and I used a 192 megahertz for 78192. There's a little harmonic mixer that you can see right here. And that's just butted right up into the dish. This piece of waveguide, boom, out to the dish, because everything is lossy at these frequencies. And then the IF, this is all like VHF coming out of this thing. These were convenient frequencies for a brick oscillator, I believe, from the Nixon administration that was still operating. You know, I think it ran 7.8 gigahertz, and that's what I used for the LO multiplied up. Yeah, it's basically all math at this point. If you can add and subtract, you look at what you've got in the junk box and say, oh, I can come up with this number that's between 70 megahertz and 6 gigahertz. Yeah, that'll work. I've got this SDR. So that's the best part about this, though, was having a frequency display that says 47,088,100.00. That's just cool. You can see it right there on the. Right. Okay. All right. So I got into this, and I'm thinking to myself, well, we got these people doing all this cool harmonic mixing stuff. I'm thinking to myself, could I put a Pluto SDR at 10 gigahertz directly? I mean, no transverter, just this thing, right? And what would it take, you know, to get signal levels up and to be able to hear, right? Obviously, I'm going to have to add some filtering and some amplifiers and things like that. But I either have those or I can find them. I can either go out to eBay and pay an arm and a leg, or you live in Rochester. There are lots of people here who have this kind of stuff, and they're very willing to share to help people get on microwaves. The idea here is that we're just going to build a direct conversion 10 gigahertz SDR, right? I'm going to run this thing at 10 gigahertz, deal with whatever losses there are in there, and see where we come out. The question I had was, is this any more than a lab toy? I can find people doing this on YouTube and stuff, but can you actually work DX with this? Can I get across the room? All right. We already talked about the aliasing, right? So I can run this thing at a subharmonic and use, you know, odd multiple harmonic to get energy at least up at 10 gigahertz. We did it for receive when we did the antenna range, but the transmit works the same way. Now, I'll obviously want to get rid of all the low frequency stuff that I don't want to come out, and I just want to isolate the 10 gigahertz signal. So we just want to filter it out the aliases you don't want. We know it's going to be lossy. Remember, the 809363 is only spec'd to 3.8 gigahertz. Goodness knows what the input looks like at 10 gigahertz. All right, I guarantee you it's not anywhere close to 50 ohms. What's worse is the board's made out of FR4. They never had any dreams of anybody trying to use it up here. So this is a lossy material to use. You remember those pictures? There's strip line that goes to the SMA connectors. I'm sure that those SMA connectors are top dollar for 10 gigahertz. I mean, there's all kinds of things that are unknowns in the system. We haven't even talked about phase noise. I'm not going to worry about it. Can it be anywhere in the ballpark of a normal transverter-based system? All right, so here's the challenge. Pluto puts out about minus 30 dBm. Now, those of you who are very good with decibels, how much power is that in watts? Try again. It's 1 microwatt, give or take, right? 30 decibels down from 1 milliwatt. That's the energy we're starting with. Going the other way, we supposedly have about a 30 dB noise figure on receive, and that's only ancillary measurements that other people have made. I think it's optimistic, having gone through this. I actually think it's worse than that. Phase noise, yeah, it might be an issue. A lot of that's based on the clock that I put in. Basically, phase noise is an issue when you have interfering signals. So out-of-band interfering signals are going to cause noise where I'm trying to listen. That's basically what it means. I'm going to need to filter, right? Got to keep things out of the receive chain, only the frequencies that I'm interested in. So here's what I set up. All right, this is not complicated. Transmit and receive ports on the Pluto, transmit chain, we put it into a piece of waveguide. What's a piece of waveguide? This is a piece of waveguide. Coax connector goes in here, there's an electrical quarter wave inside. By the magic of RF, this thing will propagate down that rectangle with very, very low loss until it comes to the other end of the waveguide. All right, coax in, waveguide transmission line, coax out. This is what I did in the transmit chain right here. All right, now why would I do this? Well, remember our earlier slide, waveguide's a really good high pass filter. And it turns out 2, 3, 5 gigahertz is not getting through this. All right, it's going to have, you're going to get more leakage around the connector than you are going through there. So that's what we did. It just makes kind of a wide bandpass filter. This will pass about 8 gigs to 12 gigs, something like that. So 10 gigahertz is right in the middle, right? So I did that both in the receive and transmit chain, all right? Don't have waveguide? You can make your own. This is 1/4-inch pipe. This is what I used on the other side. It's 3/4-inch pipe with an SMA connector in there, right? Turns out it's waveguide, right, that you can get at Home Depot. In fact, McMaster Carr has a great brass waveguide section if you ever want to go there. On the receive side, so I use a lot of gain. I had a 2-stage old W5LUA preamp. That one was probably made in about 1988, but it still works. And I used another surplus amp, or they use a demi amp? Yeah, I used the demi amp here. About 38 dB a gain in the receive chain. They're both low noise. Really, the first one's the only one that matters. And this is how I set it up. By the way, I use the same TWT you saw in the picture there. You get a lot of gain out of those, so if you have one, it's a nice way to get a lot of power from a very, very small amount of power. If you don't mind high voltage outside on a tripod. Great question. This is a coaxial relay. It's a coaxial transfer relay. I don't actually have the specs on this, but it hasn't blown up yet. So it's an SMA transfer relay. It's got 4 ports, break before make. Very important. That keeps the goes out and out of the goes into. And you know, so it connects these 2 ports or it connects these 2 ports, right? They're pretty easy to find surplus. They're cheaper if you don't mind dealing with like 28 volts or something like that. You want to find a 12-volt one. They're a little more in demand. But that's all it is. A lot of those relays at 10 gigahertz are, you know, they're rated at 20 watts or so. I'm probably on the edge here. You play with these things, sometimes you dance with the devil. It hasn't broken yet. So how did the transmit side work? This worked great. This was awesome, right? Gain is cheap, right? Start with a little signal, blow it up, power's coming out. The receive side. Turns out it was almost good. Like, I could work people with this. I mean, I easily work with the guys out in Toronto. It wasn't quite there to my other system. I did a little MDS test with it, and I'm basically about 3 dB short with this setup. And what I think happened was I don't have enough gain in the receive chain. If I just had a few more dB, I'd be able to hear that noise floor where it is on the other radio. So I think this is actually doable. The way I knew this is I turn on the power to the preamps, and the noise floor of the receiver didn't really change. Like, it should change. I should have conversion gain coming up when I turn on the preamp. You guys know this on an HF radio. You turn on the preamp, it gets louder. That's what's supposed to happen. That wasn't happening. So I know I was short on the gain side. When I get back to this, I'll probably just put a different preamp in there and see if I can make it work. So I actually think this is doable. Again, I mean, it's DIY. You got to be willing to deal with some parts. But if you probably want to shield the Pluto, you know, this is not. Definitely at 10 gigahertz. You do not want a plastic case and a PC board flopping in the breeze. The software I was using the 5th harmonic alias. That was just because of some convenience for the developer, not having to do crazy math with a sideband turning over. Turns out you can actually get 6 to 8 dB better if you use 3 gigahertz as the LO as opposed to using 2 gigahertz. I think that would probably get me my 3 dB on receive. I don't know yet. I haven't tried it. Beyond that, you're probably looking at hardware modifications. Those balance that you saw on the PC board, those are rated to 6 gigahertz. We're basically an octave outside of their design range. I'm sure they're very lossy. Replacing those would probably get you something. All right, so that's what I have here. Now, what I'd like to do, at least for the people in the room, I can set up the little antenna range here. You can actually try holding the antenna if you want. Kind of see how that works with the software. I do want to entertain questions though from the room here, people online, as we go through. So, yeah. I'll repeat. Did I get any QSL cards? Oh yeah. So most of that's done logbook of the world. Now, most of the microwave guys are doing QSL cards. Now, special QSOs, right? Really cool DX, memorable contacts, things like that. Yeah, we'll certainly exchange QSL cards. Absolutely. What else? Okay, so if you wanna buy one of these off of DigiKey, last I looked, it was $230. You got to ask yourself if you get $230 of learning out of something. That's usually how I justify something in that range. It's not an impulse buy, but
Yeah. I'm not familiar with working up at these frequencies, but you did mention that you were able, with your antenna, to just move it around and find contacts.
yeah,
Is
that's
that
not normal.
right? What do you normally do to make
Yeah,
contacts?
usually there's some sort of prearrangement. So that'll be either online. Cell phones are usually texting. Texting is a common way to do that. It used to be in the old days we'd use like 2 meters or something like that as a liaison frequency. Right. So it used to be we used 2 meters as a liaison frequency. The problem is the gear is so good, I can talk a lot further on 10 gigahertz than I ever can on 2 meters. And it sounds a little bit crazy, but that actually is the truth. It would, during the summer, on a summer morning, it would be no problem working another 2-watt, 2-foot dish on the other end of Lake Erie from my driveway. Now, I have a really good view. I mean, I'm looking over the Genesee Valley. So you want to be in a location where you got a good horizon, but that's actually fairly typical now with today's stations. I'd have a hard time doing that on 2 meters. I mean, yeah, you could probably do it, but am I going to go take a 10-foot boom Yagi with me, with my tripod, just to set that up in a PA with and the batteries to go with it? Probably not. It actually fell out from the fact that people could that the microwave stations could just work so far that actually fell out of favor. It got in the way. People weren't going out because they needed it, and it was too much equipment. So, go figure, right? I mean, that's we'll be there. Yeah. So the question is, I mentioned that you can do complete homebrew, waveguide, things like that. Most of what I do is I'll pick up stuff at a ham radio flea market. So if you know what you're looking for, especially in the upstate New York area, there's actually a lot of this stuff that you can find at a flea market. This here is a piece of waveguide, but it's funny. It's got stuff in the middle and tuning screws. This is a filter. Originally, it was a filter for, it says on here, 10.6475 gigahertz. I don't know what was up there, maybe a radar application. Probably not radar, but whatever. Somebody retuned this for the amateur band at 10.368 gigahertz. Now, I'm looking at this thing. Somebody took a lot of time to do that. Somebody had to sit with a network analyzer for a while to kind of watch this thing and get it down. I can't. That had to be mind-numbing. But fortunately, I found one that somebody already took the time to do that. So that's a nice little part to have. I mean, it's a better filter than just plain waveguide, right? You'll find amplifiers, surplus amplifiers. A lot of stuff coming out of satellite service are great. You can actually you can take apart an LNB. I've never done this, but you can take apart like a DirecTV type service LNB designed for 12 gigahertz. A lot of those, if you can even keep them in the case. Some of them, you can just take out the part where the output of the LNA before it goes to whatever mixer frequency converter is in there, and just use the LNA board and use that as a preamp. And if you can get that working, they're actually pretty good. I mean, these things are designed to point up in the sky where you want a real low noise LNA because there's nothing up there. A lot of those have noise figures around a dB or so at 10 gig, which is really quite good. Some are even better. So that's one thing you can do. You got to be good with an iron. Probably want to deal with surface mount parts. That's what it is. But you can find things with SMA in, SMA out. I don't know if I brought any. I don't know if I brought a little surplus amp around here or not. I don't think I did. But that's you look for those things. What usually happens, I end up looking at a flea market. I see something that's got an SMA connector on one side, an SMA connector on the other, and I look at what is it. Try to. It's a little bit of. Sometimes it's a guessing game. You got to take it home and figure out what it is. But $5 of learning, sure, I'll do that. You know, that's what flea markets are for. Online, you can find stuff too. It'll be a little more expensive, obviously, there, but if you know what you're looking for, sometimes you can find it. Dayton's really good. Probably not as good as it used to be, but I found a lot of things at Dayton. Oh, okay. So what kind of quality checks do you do when you're home brewing microwave stuff? Usually, try it till it works. The only time I think, there are bad SMA connectors, like adapters, or it can be a nightmare. For example, at 10 gigahertz, you generally want to avoid right angle connectors because they're not constant impedance. There's usually a right angle in there somewhere. Some might be okay, but you don't know. Usually the ones that are swept, they look like macaroni. Those are usually going to be better. The problem is now there's so much Chinesium out there, they might have used wood as the center insulator or something. How do you know? Yeah, so buying surplus, because good surplus is going to have the name on it. That's one way to do it. To find a good quality connector. There are people here who can sweep these things. All you need is a power meter, something to measure power. I think you might be able to do relative comparison with a Pluto, using it in that sort of VNA mode. Use some VNA software. You could probably see, a difference of half a dB pretty easily, and that's what you would care about. So yeah, when you get into microwave materials, you start, like you talk about circuit board material, that stuff tends to be a little, maybe it's not so bad anymore. You can get some of the Rogers PC board material. If you like to actually you want to design a circuit on a board and have it fabbed, you can get high frequency stuff out of PCBWay and some of that stuff. You know your board materials. I'm not an expert in that. You can spec it out. It's still probably going to be, a glass fiberglassy type thing, but it'll be better. It'll be a thinner material. 10 gigahertz, not so bad. You're probably not going to be home brewing above that. You're starting to get into wire bonded components, and that's surplus land there, and pretty hard to find actually. Yeah, some people strip microwave transistors if you know what you're looking for, like a microwave PA transistor. There's a hot Chinese market in that. If you want, some of them are genuine even. Most aren't. Yeah, so that can be a little bit tricky. Genuine fakes. Yeah, genuine fakes. Yeah, it's an issue. It's nice to have something that you can measure parts with. Sometimes you just start with something and try it, and it works okay. And then when you come across something better, you put it in and see if you got an improvement. A lot of things are that way. None of these systems are perfect. You start with something simple and work your way up. Thanks everybody for paying attention. I know it was a whirlwind. So.